So we've posed the question, why does that beam and chain system undergo simple harmonic motion, or does it? Now, the beam and chain just means we've got a rotating beam up here. And we got a pulley here. And the pulley is attached to another pulley, and there's a chain. Going down to the floor here, and there's a chain over here that doesn't go down to the floor. And there's a bunch of chain piled up on the floor over here. Okay. So when enough chain gets piled up on the floor, this chain's going to be heavier than this chain. This chain's going to exert more mass, more force than this chain, because the part of the chain on the floor is not exerting any force on the system. You know, this is a very schematic diagram, but everybody knows the system. So we have a chain that's basically descending on this side, causing this beam to rotate faster and faster until too much chain piles up here, it slows down, and then whatever chain you got over here exceeds the chain over here that isn't on the floor, and it starts rotating the other way. And it keeps going for a couple of revolutions. Another thing is, when we look at the graph, I was a little surprised that there was as much damping as I thought there was. I figured it'd go half a dozen rotations before it came to rest, and it only went through about not even 3 cycles. So what you had was a graph that looks something like this. I think when I looked at your data, okay? So in the first place, this is not simple harmonic motion. This is damped simple harmonic motion, which I'm not going to ask you to analyze in this course. I did mention that those who are taking differential equations can solve that equation, okay? I'll write it down for you at the end of class and append it onto the video if you want me to. Just comes down to the net force. Well, I'm not going to say that yet. I'll come back to it in a minute because I want to keep the answer to my question unknown for a minute, okay? So when I ask, why does it undergo simple harmonic motion, or does it? Well, first place, it sort of does, but not really. It's actually damped simple harmonic motion. If you had a pendulum, it would be a lot closer to simple harmonic motion. Remember the physical pendulum that we had, the beam rotating in a vertical plane when you put magnets at different places, and you looked at that motion, that was very close to ideal simple harmonic motion. It was still damped, but the damping would be hard to identify over a handful of cycles because the thing kept going. I mean, the thing went through 100 revolutions or something, or 100 oscillations, and it was still going pretty good. Okay, that one is closer to being simple harmonic motion than this is. It's still damped, but not much. Ideally, you don't have any damping and you have a constant amplitude. Your peaks and valleys all go the same distance on the other side of equilibrium. Okay, so people are saying, well, because it has a constant energy and keeps going from potential to kinetic and back, that's not why it undergoes simple harmonic motion. Actually, it could be taken as a definition, okay? But it has to go over and back in a certain way. And it's a lot more complicated. Although it's a really good insight. Everybody should know that after doing the problem set. And as I say, I haven't had a chance to look at the problem set, which just came in last night. Okay. So what's the bottom line? When we started simple harmonic motion, even earlier in the semester when we were anticipating simple harmonic motion, bottom line is F net equals negative KF which leads you to the differential equation mx double dot equals negative kx. So x equals a cosine omega t plus phi. Those of you who are taking differential equations would solve this equation. I saw you solve the equation using the characteristic equation, which is fine. If you haven't had it, Lucas, we don't want to leave you out in the ozone. All you got to do is plug this in here and verify that it works. You got to know how to do that. It's almost certain to be on the test in one form or another. Okay. The analogous is that net torque equals negative kappa times theta. Kappa is just like a Greek K. I make it a little bit different, but it looks very much like a K. You can see it in the kind of summary that I posted where I do use the kappa. And the other thing, omega is the square root of K over M. You get that just by dividing both sides of this equation by M, right? And in this case, omega is the square root of kappa over I. This is for physical pendulum. The beam and chain system. Okay. I also mentioned that the chain has a moment of inertia. The amount of chain suspended on this thing, okay? Total amount of chain that's moving is constant. And the mass of that chain gives you moment of inertia, IR squared, where R is the radius of this pulley in here. Because the force exerted by the chain is transmitted, what force exerted by each chain is transmitted to one of the other pulleys here, one of the two pulleys along a line that's tangent to that pulley at a distance of 2.5 centimeters from one pulley, 5 centimeters for the other. Okay? We talked about that. It's something you want to ponder. It's a little difficult to understand that. That was challenging, but it's a line of force of the line of the force exerted by the chain doesn't impact the system until it gets to the pulley, at which point it's like, here's your pulley and here's your force. Here's your R vector, here's your force vector. Assuming this is your net force, which isn't right quite true, how net equals R cross F net. As I've drawn it here, what's the direction of tau net? Point in the direction of tau net. Okay, I see. Yeah, you're both using your right hand. Looks left to me when I look out there. But your thumb was in the right direction. R cross F into the board. It's a direction of the net torque. And now the main point is this is your premise, either this or this, and they are mathematically equivalent. You just got to remember to use torque here or moment of inertia and theta as your position function. Okay. And everything else follows, every bit of it. And we did that in class within the last couple of weeks. Okay, develop the whole thing. Try to understand how all that comes out of this, or equivalently out of this, but at least understand this and believe this. Okay, that's all right. If you understand this and believe this, then in the future, if you need to know the details of this, it'll be easy. Okay, but you got to understand at least for the force. So I want to look a little bit more at why simple harmonic motion tends to occur for different systems. This one's a little different than the systems you usually see, but we had the equipment set up and it was so compelling that we did that. Okay. Another thing I could have done incidentally was hang two metal cylinders, thin metal cylinders, like a metal dowel, 1/8 of an inch in diameter, something like that, into water on this side and into nothing on this side. Okay. The blowing force of the water as the cylinder descends into the water is linear with how far it's descended. It descends, for every centimeter it descends, you get a certain amount of blowing force because there's a certain amount of that cylinder displacing the water. Now we haven't gotten to the fluids and buoyancy and so forth, but the buoyancy of this thing will cause it to move in simple harmonic motion. I haven't had a chance to set that up. I kind of want to, and we'll probably do that when we get into fluids very early in the next term. Okay, because it's pretty neat. One of the neatest things. We'll see how that works. That would give you a net force that's equal to negative kx. If x is how far the thing moves this way, well, that's going to be proportional to how far the beam travels. Okay. And the deeper the beam goes, the more buoyant force the water gives you. And it is of this nature, and it's very, very even, very constant. Very, 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 yeah. And that force is very much a constant multiple of your position. It's got to be a restoring force, incidentally. If you don't have a negative there, you're into something completely different. Not simple harmonic motion. Nothing's being restored. Got a question? Okay, question about the difference between K and kappa. Are they the same thing? They have the same function, but if you look at the fact that K is what you multiply by position to get net force, you find that K has to be in units of newtons per meter, let's say. Units of force over length, okay? Could be dynes per centimeter. You know, some unit of force over unit of length. Could be pounds per mile, okay? Any unit of force over any unit of position will give you a K. Down here, theta is in radians. Tau net is in meter newtons. Newton meters. Okay. And I'd say meter newtons instead of Newton meters because you don't want to think joules. Okay. So I'll put the meter in front just to distinguish. I don't know if your text does that. I don't know if you want to do that, but I think it's a good idea. Anyhow, it's going to then have units of meter newtons per radian. Of course, a meter per radian is just a meter. So in any case, it's going to have units of meter newtons. And if you divide that by units of I, which would be kilogram meter squared, you end up with reciprocal seconds, which is the unit of omega, because omega is your angular frequency, the angular velocity on your reference circle. Okay. And that connection is simply here's your reference circle. Your reference point is moving around here, angular velocity omega at distance circle radius A. Angular velocity omega, a motion that you should be very, very familiar with, since almost everything we do in the lab comes down to something moving in a circle, or at least, half of it anyway. Angular velocity omega, which we also call the angular frequency when we use it in one of these equations. Now, this thing's moving around at angular velocity omega, so that x equals cosine of omega t. X equals a cosine of omega t. If it starts here. Now, if it starts here at some angle phi, then you have an omega t plus phi. And that's all the phi means. It means where do you start your timer? Do you start your timer when the thing is here, starting to move back this way? Or do you start your timer at some other point because maybe this thing's just sitting there at some non-equilibrium point and you hit it with a hammer and it starts oscillating from that point. So your t equals 0 would occur somewhere besides here. Now at the end of the video I did the day I had to miss, talk about that reference circle, okay? You want to take a good look at that if you haven't. Okay. Okay, well. Yeah, I'll just draw a picture right here of why a pendulum undergoes simple harmonic motion. Here's your simple pendulum. Here's vertical. And the forces acting on your pendulum are mg, and you could say negative mg times the j vector, and tension in the string. For small oscillations, the tension in the string has a magnitude very close to mg, so that your net force, I'm looking for the right color, dx is this vector here, which is approximately equal to mg over L times x. So omega equals the square root of mg over L, and you have this motion. Now, if the thing goes too far from equilibrium, the tension, magnitude of the tension is not any longer very close to the magnitude of mg. So it's not perfect simple harmonic motion. So if you're letting the pendulum swing way out, the period's going to be a little bit different than if you let it do a small oscillation. Something you can understand, I'm sure your book explains it too. Or you can just let AI explain it to you if you want to get a different explanation. One thing about AI is don't let it explain things to you while you're trying to work out a problem, because then AI is working the problem for you. Get the explanation before you work the problem. Make sure you understand it well enough to apply it to the problem, preferably at least an hour after you've looked at it. So you pull it out of your memory and start retaining it, okay? Just advice on how to learn by doing the homework. Okay. And then a mass on a spring is pretty obvious. It's standard. Your book explains that real well. You want to understand all that. Okay, well, get a little far away from my original intent, which was to talk about a lot of systems. Now, in doing the exam, making up the exam, my model right now, and I'll tell you more on Wednesday when I've had more time to actually work on it, because right now I'm just creating a bunch of really complicated off-the-wall problems I'm going to have to simplify, okay? But looking at the situations I want to ask you about it, half of it's going to be situations you've directly observed in the lab. And I want you to understand those in terms of the data you've taken, in terms of things you've seen, okay? At least half the exam, approximately half the exam is going to be in that. The other half is going to be in problems that involve exactly the same knowledge that you would have used in doing the homework. Okay? So if you didn't really develop and lock in the knowledge when you were doing your homework, and that's typical. I mean, I did a lot of homework in my first physics class, where I just looked at an example and imitated it until things started to sink in. Or, about half the problems, the answers were in the back of the book, as is the case with yours. And I worked backwards from the solutions. That's how I started learning physics. Okay. Yeah, the learning process got a little more sophisticated as I went on, up to my limit of sophistication, whatever that happens to be. Okay. But it's just a little advice that's something you want to kind of keep in mind as you're learning things. Okay. Okay, now am I recording or am I not? The thing doesn't show me. I guess I was. Okay. Okay, so let's think about situations. Okay, you have the one where the cart goes up the incline and back down, right? You got a lot of data for the cart going up the incline, but I think a lot of times you stop there. And that was, when I had to leave lab early, couldn't supervise and make sure you were doing the thing both ways, which is where the real guts of the problem are, but you can still understand it. Because I came in here last time, moved the cart up and down the incline and counted 1,001, 1,002, took 6 seconds to go up and 8 seconds to come back or something like that. There was a clear difference in the time it took to go up and come back. Okay? A couple of things about that. If the incline is too steep, I'm not going to be able to tell the difference between up and back, because the acceleration or the contribution to the net force of the rolling friction becomes a smaller and smaller percentage of the net force. Because the steeper the incline goes, the greater the component of the gravitational force parallel to the incline. The frictional force actually decreases as the ramp becomes steeper, and it becomes insignificant. So unless you had extremely good instrumentation, you would not be able to distinguish between how long it takes to go up and how long it takes to come back. Counting 1001, 1002, etc. I couldn't tell exactly when the thing came to rest because it was moving very slowly before it came to rest. But I made my best estimate, and I wasn't off by 2 seconds in the instant where it came to rest. Okay, so I got reasonably good results because the ramp had very little slope. So that the frictional force was much greater compared to the gravitational component of the force down the incline than it would be if the incline was steeper. That's an important point, and I'm not going to write it down. Maybe I'll publish a transcript. I'll go to the transcript and get that sequence of words and put it down. But it's also something you kind of want to think about in here. So what's the situation there? The situation is you've got an incline. You've got a cart. Low friction. We've got a small incline. Well, if we just consider the cart to be a point, then gravitational force is mg. We impose an x and a y coordinate system. Now on the midterm exam, I saw a lot of people make an x horizontal and y vertical. Okay. You don't want to do that because if x is horizontal and y is vertical, you've got a bunch of forces, the normal force, the frictional force, the component of gravity down the incline. None of those is parallel to any axis. The only thing that's parallel to an axis is mg. Okay. It's much simpler. You can keep your x-axis here and your y-axis here, which means I should have labeled mg on the other side. That naturally I wasn't anticipating. Why would I do that? Okay. Here's your y-axis. Here's your mg. You project at a right angle to the y-axis. You project at a right angle to the x-axis, and you get the x and y components of mg. I'm not going to do the trigonometry for you. The trigonometry is pretty obvious. If this is at angle theta, then this angle is theta. Okay? And make sure you're straight on that. Make sure you're careful about how you do that. Because I tend to believe that people haven't done as much trigonometry as maybe they could have by the time they get to this course, if they'd had more rigorous courses in their first trigonometry. Okay. But still, you've got enough trigonometry. Trigonometry here is the early part of a good trigonometry course, just right angle trig. But you got to be able to visualize it with rotating coordinate systems and stuff like that, and that can be challenging. Okay, so make sure you meet that challenge. Okay, so what we then have is the force mg sub x. That's the component of the gravitational force along the incline, and that's what accelerates whatever's on the incline, or tends to accelerate whatever's on the incline. If your incline is steep enough that you overcome rolling friction, then the thing is going to roll in this direction or this direction if it's given just a little nudge in that direction. Now, if it's going up the incline, it's going to roll a little bit, but it's going to stop and turn around and come back down because the incline is steep enough that this overcomes your rolling friction. Okay. Now, you do have a normal force. And it's equal and opposite to the y component of mg. So we replace mg by mgx and mgy. And then just to emphasize that we've replaced it, we draw a little wavy line through it to say, okay, this is gone. Now we just have this and this. It's just like you have some rubber bands. Somebody's pulling in this direction, somebody's pulling in this direction, and somebody else needs to pull in this direction to keep this thing, well, to keep the net force in this direction. I didn't quite say that right, but you get the idea. Just think of how you would simulate this with rubber bands. If you did this and had one force in this direction and equal and opposite force in this direction, then in order to get the thing to move in the direction that corresponds to the plane, you'd have to be pulling with this force here. Okay, well, then you also have force of friction equals mu times your normal force. If you're moving downward, and that tends to reduce the effect of the parallel component parallel to the incline of the gravitational force. It's fighting the effect of your gravitational force to pull the thing down the incline. If you're moving upward, I'm not going to draw the picture, but if you're moving upward, friction is in this direction, and it's reinforcing the tendency of the parallel component of the gravitational force to slow the thing down. Okay? So it's going to slow down faster than it speeds up. If it goes up the incline and goes back down, it's going to slow down. As it comes down more slowly than it does when it moves up. So that the picture comes down to this. If your velocity is in this direction, I have a lot of trouble finding my colors here. Okay, then here's your picture. So here's your F net. You add this vector to this vector, and you get a shorter vector down the incline. Moving up the incline, you have your parallel component of the gravitational force. You have the frictional component, which is equal and opposite to this, since friction acts in the direction opposite motion. And your net force is like so. The net force, if you're moving up the incline and the net force is down the incline, then it's going to slow you down. You have a deceleration, an acceleration in the direction opposite motion. If it's moving down the incline, then you got a smaller net force still in the direction down the incline, and it's speeding the thing up because the net force is in the same direction as the velocity. Now that's something you really need to sort out because there's almost certainly going to be a question on that since that's a system that we observed. Now, when we observed that system, we were accelerating the cart from down here with a magnet strapped to the end of the cart and another stationary magnet. We brought the cart into the vicinity of that stationary magnet, measured how close we were, and released the thing and saw how far it goes up the incline, right? And by putting a very similar pair of magnets on the balance, we came up with some pretty good data. X being separation, F being the force of the magnet. What can we do with this graph to figure out the change in the kinetic energy of the cart between position X1 and position X2? Let's talk about that for a minute. Okay, so again, I asked, how do you find the change in kinetic energy? And I got a very good answer: integrate force with respect to position. Okay. I'll say integrate f of x with respect to x from x1 to x2. Okay, now the first answer I got when I said that, okay, that's fine, but this function is just a curve that we drew to fit our measured data, our empirical data. You can't come up with a good function that matches this curve. I can't come up with a good function that matches this curve. I could do a bunch of piecewise quadratic approximations or exponential approximations or whatever over small intervals and get something pretty close. But that would be really cumbersome and probably no better than what you can do by simply using the graph intelligently. Okay, so first suggestion I got, you got to use a graph, one way or the other. You've got to use a graph with this curve that maybe you've let Excel, do a running average or something like that. Okay, because there's no function in Excel. It's going to give you a good match. I don't think there's any function anywhere that gives you a good match. If you've got enough multivariable calculus, you could try integrating all the dipoles over the dimensions of the magnets. That'd be an interesting thing to do, but I've never had a class that really got to the point of being able to do that. And I've never done it because it's kind of cumbersome and have to go to a computer to do the thing. And I know how to do that, but it's so inelegant that I can't bring myself to do it. Okay, well, anyhow, basically, you got to find the area under this curve. Okay, a couple of ways to find the area under the curve. The first suggestion I got was, well, use a trapezoid to approximate it. Okay, so trapezoidal approximation. You know this dimension, you know this dimension, you know this width, so you can find the area, right? Use the trapezoid. Well, what percent of the area do you think you have to subtract? What percent of the area under the trapezoid is not under the curve? You think 20%, 10%, 5%? Hold up fingers. What percent? A lot of people are saying 5. I'd say it's between 5 and 10. Okay. And nobody wants to hold up 2 hands. That's too much trouble. Okay. I just did. No, I'll have to recover for a week. Okay. Now, you could do that and you could make a pretty good estimate, but there is curvature here. Okay. Well, the other thing you could do is you could reduce that effect by doing 2 trapezoids. Now, what percent of the, it's around 1% probably. You've reduced the uncertainty or the error, whatever, to the point where maybe on this interval, 2 trapezoids is good enough. Because remember, you have empirical data, okay? 2 trapezoids might give you within 1%, if you've got a well-drawn curve, of an accurate answer. But if you want it more accurate, you could do 4 trapezoids or 500. Well, that would be overkill. 500 trapezoids when your data have a significant amount of uncertainty anyway, going to be pointless. Anything over 4 trapezoids would be pointless given the way we measured these forces. And I think 2 trapezoids would be perfectly sufficient, but 1 trapezoid I don't think is enough. Does that make sense? Now that's the kind of sense and the kind of thinking that I really want you to have some handle on. At least understand that if you use 2 trapezoids, this gets much more accurate than if you use 1 trapezoid. Okay. And that's something you should be able to relate back to what you learned in your calculus course. Another option would be to estimate your average value. Your average value is a value that misses as much of the area under the curve over here as it includes over here. So the average value estimate, let's say I want to use something to contrast a little better. Okay. Okay, so I could try an average value estimate here. Average value, it misses this much area, but it includes this much area. Now you can see that the area that's included under the average value line is greater than the area that you miss. It's under the curve, right? So you're going to have to lower it a little bit. You don't have to go too far because this area is going to start increasing pretty rapidly. And this area is going to start decreasing pretty rapidly as you lower the average line. Okay? This one includes more than it misses. Okay? If you lower the line, you get it to where it includes about as much as it misses. Does that make sense? Can you see that? You understand those words? Then the work done by the magnetic force would be average force times delta X. Now, what I saw on the midterm, I'm trying to remember what it was I saw. I'm not, it's something I'd kind of like to forget, except you need to know. If you have a table of these things, of these values, you know this point, this point, this point, this point, this point, and so forth. Well, what you want to do is, if this is F1, F2, and you got positions X1, X2, X3, and X4, you do a pretty good approximation by essentially doing a trapezoid in each one of these intervals. Okay? Or maybe F average on each interval, right? So you do sum of your F average delta X's, which would be approximately equal to F1 plus F2 over 2 times X2 minus X1. That would correspond pretty closely. Be a little bit of an overestimate because of the concavity of the curve. But this would not be a bad approximation. Does that make sense? Can you read what I wrote? I wrote F1 plus F2 divided by 2 times X2 minus X1. Because what are the dimensions of this trapezoid? Well, making this trapezoid a little bigger so I can label it. The width is X2 minus X1. And the average height, this height here is F1. This height is F2. F average is approximately the average of F1 and F2. Does that make sense? Should make sense. If it doesn't, look at it until it does. And then it would be like F2 plus F3 over 2 times X3 minus X2. Which would be like your second trapezoid. And what you're doing in each case is you're multiplying the average force by the interval over which it applies, okay? And what people were doing, even people who attempted to do this, is they were multiplying some average force by a distance that didn't correspond to the average force, okay? You understand that this average force is a good approximation over this first interval. And this average force is a good approximation over the second interval. We don't want to multiply this average force by the interval from here to infinity. Okay? So some people were very close to calculating this right, but not completely understanding what needed to be done. So it's kind of important to be able to do that and be able to understand the energy exchanges. Now, of course, we've got things like the work energy theorem. Over some interval, the work done by the net force is change in kinetic energy. You've got work by the net force equals work mod conservative plus work conservative. The work done by the conservative force is equal and opposite to the change in potential energy. And the net work is delta K. And then this is generally written work by non-conservative forces equals delta K. Got a bad spot on the board there. Plus delta U. Comes down to this. And this breakdown and understanding what change in potential energy is, I've defined it as being equal and opposite to the work done by net force. If you have those principles and have them straight, you're not going to screw this up. Now, if you just know this formula, it's okay if you know how to apply it. But if you understand all of this, you understand that delta U is equal and opposite to the work done by the conservative force. And the reasons for this go back to the fact that the work done by your net force is broken into the work done by non-conservative and work done by conservative forces. Part of your net force is conservative, part is non-conservative. So this is a no-brainer. This is a connection from the definition that I used for change in potential energy. Okay. And change in potential energy is not MGH. Unless you happen to be in the surface, vicinity of the surface of the Earth, and the net force is to the gravitational force. Okay. Sometimes it's what? The delta U. Well, you can equal MGH. You can equal 1/2 kx squared. You can equal big G, big M over R, negative. And more. What is it for the magnet? You can't express it as a formula, okay? You have to take your graph, your data, and make your best approximation based on your force versus separation data. Okay. Then, when you accelerate this cart up the incline, if you happen to know the coefficient of rolling friction, happen to have measured it, and then observe how far it goes from each separation. In other words, you pull the magnets into proximity x1, release it, and you figure out the area under this curve until it becomes insignificant, which it does fairly quickly. Okay. And you can make a comparison between energies, comparison with forces, et cetera, and you can completely analyze this if you have this information, which if I put it on the exam, I'll give you in the same form I did on the midterm, in the form of a table or form of respective values of force and position. There are not a lot of them. 4 or 5 values pretty much allows you to approximate this curve. If it's on the exam, you're going to approximate it with a hand sketch. And you're going to show me how you would calculate it based on that sketch. Okay. Change of potential energy between x1 and x2 is this. Change of potential energy between x2 and x3 is this, because the magnet force is conservative. There's also a little bit of potential energy change due to the incline, and you're going to want to be able to pull that in as well. But that's an important system to understand. Okay. Well, we don't have any more time, but that's a good start. Now, you understand that there are basic principles. Okay, the main ones that we talked about today are that simple harmonic motion occurs when your net force is a linear restoring force, F net equals negative kx, or your net torque is linear function of your angular displacement, right? Everything else follows, and the circular model is a good one. Keep that in mind. This situation, there's a lot of detail here. You got to be able to analyze the forces. You got to know what the force down the incline is. And you got to be able to calculate the frictional force. based on data like 6 seconds up, 8 seconds down. You should appreciate the fact that if you put the incline too steep, you're not going to be able to tell what the difference in those two times is. Even if you got a string over a pulley and good data, there's still a little ambiguity where the peak of that curve is. Okay, there's a little mathematics you can pull out to do that. If it's a parabola, you can actually come up with a very good function modeling it. I'm probably not going to lay that on you. Okay. Think about the other principles. Go back over the thing that I posted a couple of weeks ago, which has been updated. Think about where the principles are, the ideas and equations and formulas, everything else follows from. Okay, I'm going to kind of survey that next time.